The insane engineering of the Concorde. Hello and welcome back to Bite Me. Before we start, I would like you to hit that red subscribe button so that you never miss out on any of our videos. In 1969, a pioneering vision of the future made its debut to the public. In a few years' time, the sight of the Concorde on international airfields all over the world will be commonplace if all goes well, and there will be 130 passengers on board. Flying times will be cut by half, London to New York from 7 hours 40 minutes to 3 hours 20 minutes. The juxtaposition between this dated footage and the futuristic plane is strange. It's hard to believe passengers 40 years ago in time, when color TV was a luxury, were flying across the Atlantic at the speed of sound. The Concorde was well ahead of its time, an anomaly in the history of commercial travel. A byproduct of misguided government funding, a joint effort between Britain's BAC and France's Aerospatiale, and its development funded entirely by the British and French governments to the tune of $2.8 billion. The Concorde's legacy is marked by its commercial failure, but this engineering marvel was a triumph of ingenuity. Nothing remotely close to it had flown before, and nothing like it has flown since. Turning what had been a military-only technology into a luxury flying experience required innovative thinking. This is the insane engineering of the Concorde. Intro sequence. The engineers of the Concorde had several unique challenges. Developing a supersonic plane is difficult enough with military design requirements, but developing a supersonic plane that would satisfy the wealthy customers it intended to serve is an entirely different ballgame. Aerial refueling makes fuel efficiency a secondary concern for the military. The comfort of the plane's passengers is an afterthought at best, and the price tag attached to these often limited-run specialty planes is beyond the budget of a commercial airline. Those needs are reflected in the Concorde's unique design. A sleek exterior hiding powerful engines. Engines developed from the iconic British warplane, the Afro Falcon. Fuel efficiency and supersonic flight are two opposing ideas, but these engines, the Rolls-Royce Olympus 593, when flying at Mach 2, were the most efficient engine ever created. These engines, when introduced for the Afro Falcon, were capable of generating just 49 kilonewtons of thrust, but over the course of their adaptations for use in the Concorde, increased in thrust by over triple to a whopping 169 kilonewton. 20% of this thrust increase was provided by newly fitted afterburners, a technology typically reserved for military planes. Afterburners work by injecting fuel directly into the superheated and high-pressure exhaust of the turbine section. Despite this air's journey taking it through the combustion chamber, only about half of the oxygen in the air is consumed, leaving untapped energy in the exhaust of the engines. To capture this energy, fuel can be injected directly into the exhaust of the turbine and ignited, basically acting like a rocket stage of the engine, causing further expansion and accelerations of the exhaust through the exhaust nozzle. However, the system is useless without a controllable nozzle. Typical airliner engines have a fixed nozzle, because these aircrafts are expected to be efficient at a relatively low range of subsonic speeds. But the Concorde, with its massive range of speeds, needs not one, but two controllable nozzles to adequately control the engine's power. The primary nozzle connects directly to the jet pipe's exit and consists of pedal-like structures that can close or open to vary the diameter and therefore the area of the jet's exit. When the afterburner, or reheat as the British engineers called it, was ignited, it caused a massive increase in pressure at the engine's exhaust. This increase in pressure could cause choke flow in the engine, where a high pressure zone ahead of lower pressure zones will prevent air from flowing through the engine correctly. To prevent that, the primary nozzles opens wider when the afterburner is active to decrease pressure and ensure the mass flow rate through the engine is unchanged. However, at times, we do not want to affect the flow upstream of the nozzle. The Olympus 593 was one of the world's first two-spool turbojet engines, predated only by the Pratt & Whitney J57 engine by just a couple of months. Two-spool means the engine contains two compressor sections, driven by two turbine sections, each acting on their own concentric drive shafts, allowing the two sections to operate at different rotational speeds. The high-pressure compressor was driven by the high-pressure turbine, and the low-pressure compressor was driven by the low-pressure turbine, which was the closest turbine to the primary nozzle. When the primary nozzle was actuated, it caused a pressure change across the low-pressure turbine, which would cause the low-pressure compressor to spin faster or slower. This provided a method of engine control that allowed the plane to optimize its performance across its wide speed range. The secondary nozzle functions is just as complex. The eyelet doors looks like some kind of steampunk blast shield. and for good reason. The force these secondary nozzles had to endure influenced their appearance, withstanding huge forces at both supersonic and subsonic speeds. They could even close completely on landing to function as reverse thruster. By actuating these nozzles, the plane could carefully manipulate exhaust velocity and thus maximize thrust, because together the pair acts as a controllable converging-diverging nozzle. Converging-diverging nozzles are typically used in rocket nozzles to accelerate the combustion products to the optimum speed and pressure. The opposite shapes are needed because air acts completely differently at subsonic and supersonic speeds. For example, when subsonic air travels through a converging duct, it speeds up as the cross-sectional area decreases until some critical area, which is referred to as a throat. This is where Mach 1 would be reached. At this point, no further accelerations of air can occur, as the flow is choked. Now, as you would expect, if that same subsonic air flows through a diverging duct, the air slows down as the duct area increases. This is Bernoulli's principle at play. The bizarre thing is, the exact opposite occurs when air travels at supersonic speeds. A converging duct will result in a decrease in velocity, and a diverging duct will result in acceleration. That's all for today. I hope you liked the video. If you did, make sure you hit that like button and subscribe to the channel so that you never miss any amazing videos from us.